We're going to build on our knowledge of electric force by examining the electric field. And this is going to occupy a lot of our time for the next couple of lessons. Okay. To begin, we're starting with our basic definition of what a field is. And we looked at this when we talked about gravitational fields. Okay. A field is a point in three-dimensional space where a property or quantity such as a force might be distributed. Okay. So this is important for us to remember that, okay, we looked at gravitational fields, right? And we said, we all agreed in class that, hey, if there was nothing on Earth to experience its gravity, would Earth still have gravity? And everyone said, yeah, it would, because whether there's something there to experience it or not, there's still this effect that if something ever came into the vicinity of Earth, it would experience Earth's gravity, and that's what we call a field. A force is a relationship amongst two things. One thing creating a field, and then the other thing experiencing the field, and the relationship between those two things is expressed as a force. Well, if you don't have two objects, then you can not talk about a force, because a force requires a discussion of two things. If you only have one thing, that thing is creating a field, and that's what we're going to talk about now in terms of electricity. Okay? So let's say we place a point charge, Q, onto a coordinate system, and then we bring another charge, Q2, near to it. Okay, so we've got this one charge on a coordinate system, and then we're going to bring this other guy close. Coulomb's law will tell us that they exert a force on each other, right? So they either attract or repel. But then there's more of an existential question is, how does each charge know that the other one's there, right? And the answer is, because there's an electric field that's produced by both of these charges. And when each of them enter the electric field of the other, their fields change and they experience a force. Okay, so let's say this. So this is an example of a field that you probably know very, very well. And that is, of course, a temperature field. Now, temperature isn't a vector. Temperature is just a scalar. So this is like a scalar field. But if I was to say, okay, let's take a thermometer, a very sensitive thermometer, and let's say we measured the temperature at several points in the room that you're sitting in, okay? So perhaps there's a lamp over here, and so what you would see is you might see perhaps that the temperatures kind of close to the bulb are a little bit higher, and then as you get away farther and farther from this source of heat, you'd notice, oh yeah, the temperatures kind of start to drop off as I get a little bit farther, way out, and here I am very far away, okay? And so if we were to connect all these lines, we'd have thermal lines, right? Just like we see in this little diagram here of North America. And basically what we'd end up getting is we'd get this temperature field, okay? We can do the same, very, very similar. We can do the same with electric fields and with gravitational fields, etc., etc. We can draw them out. So this is a little example that you can kind of do. It's a thought example, but we could do this. We could do this if we set up a couple students around the room. We said, okay, one student's up here, they're positive. One student up here is negative. One student down here is positive. One student down here is negative. We said, okay, now let's bring a test charge close to this array. And we can say, what's that test charge going to do if I started here? Well, if I started here, it wants to get away from this guy, and it wants to go towards this guy. So it's probably going to move something whoop, like this. Here, if I started a positive test charge here, well, it definitely wants to get away from this. So it's going to kind of zip around here and then come up here. Here, if I started it at the test charge here, it's going to want to move right towards this negative, or it's going to want to move towards this negative, and kind of depending on where it is along this diagonal, it'll move in a different way. But we can do this, and basically the point is, if I was to bring a test charge at every single point all around this array, and I was to trace the path of its motion, what I'd do is I'd create the electric field. I would be sketching out what the electric field looks like. Okay? If we place test charges all over the place, we'd end up with a lot of lines of force, and those are called electric field lines. Now, field lines you've also seen when we look at magnetic fields as well, and we'll look at them a little bit later on, but With electric fields, we can't really use iron filings like we did with magnetic fields, because those iron filings, we can really get a good sense of what the magnetic field looks like. Electric fields are very similar, but we can't do it using iron filings. We have to do it in other sneaky ways. Okay, so let's draw the electric fields for some of the following charges here. Okay, so let's say, and we're going to do these just by inspection. Okay, so we've got a positive and we've got a negative. And so what we want to do is we want to generally sketch out, okay, if I had a positive test charge, and we always use a positive test charge, and I set it right here, it would want to get away from this positive, and eventually, once it gets close enough to the negative, it's going to be attracted to the negative. If I put the positive test charge here, it just wants to get away from that positive as fast as it can. If I put a test charge here, it wants to go away from the positive and towards the negative. So we kind of get this idea that if I was to place a test charge at all these spots, this is kind of the pattern that I would see. And in fact, this is the electric field between what we call a dipole, a positive charge and a negative charge. All right, so let's take a look at these 2 point charges. This is the positive and a positive. Now, interestingly enough, we could also do a negative and a negative. It'll look a little bit different, but for the most part, let's consider what this one looks like. Here's a positive. So if I put a test charge up here, what does it want to do? Well, it wants to get away. If I put a test charge up here, it wants to get away. If I put a test charge right in the middle, what does it do? A positive test charge right in the middle probably wouldn't do a whole heck of a lot. It would probably stay put because it wants to get away from this guy, but it also wants to get away from this guy. So what you end up with is this electric field that at all points wants to get away from these 2 charges, but then right in the middle, you'll notice an absence of electric field lines. And wherever we have an absence of electric field lines, we can have a point of equilibrium. So we could have a test charge that's not affected right in the very, very center and could be held motionless. All right, let's keep on going. Here is a positive plate, and here's a negative plate. And this charge distribution will become very important in a little while. So with a positive plate and a negative plate, one of the nice things about this is, of course, any test charge that starts over here goes bink and just goes straight across, wants to get away from that positive plate as fast as it possibly can. Okay? And as it turns out, all of these electric field, this whole electric field inside of the parallel plate is what's known as a uniform electric field. So basically, it's a very, very constant electric field. It's not like this, where we'd have different forces acting on a particle at different places, right? The force that's acting on a test charge, no matter where you put it in here, is always the same, right? Here, no matter where you put that test charge, you're going to have different forces, right, because of Coulomb's law. Here, though, it's always going to be the same force, no matter where we are. And we'll show you why in a couple of lessons. This is a big hunk of cylindrical metal that's charged negative. And so the electric field for this, the electric field for this looks a little bit like, well, basically lines coming in. If I put a test charge here, it would be attracted. If I put a test charge here, it would be attracted. If I put a test charge here, it would be attracted. So almost like all kinds of lines zipping in at my cylindrical hunk of negative metal. Okay? All right. That's what the electric field looks like. That's what basically the direction of the field is. Let's talk about the strength of the electric field. This can be measured by basically saying, oh, here's the force that the test charge would experience. But because the test charge is not really there, it's just a test charge, we take that force and we divide by Q. And we say, okay, so the electric field is equal to the force that would be experienced by a test charge, but we just divide it out. Okay? So we can derive the equation, basically an equation for the field strength, basically from the perspective of the charge that's generating the field. So remember, the test charge isn't really there. So this is basically what it looks like. This formula, meh, whatever. Take a look at this. This is basically what we need to know. So the force is K Q1 test charge QT over R squared. Okay? But you have to remember, this is a field. So without this test charge there, because it's really not there, it's just a fictitious, it's like a test charge. We have to cancel this test charge out, so we have to get rid of it. And so here it is. So this is what the electric field looks like because it's being created by Q1. So it's K Q1 over R squared. And basically the same with Coulomb's law, electric field strength obeys the principle of superposition. So basically the electric field that's generated by multiple objects is just the vector sum of the individual electric fields. We need to look at an example, and here it is. Okay, so we're going to look at a simple example first, and then as always, we'll go to something more complicated in the next lesson. So here are two objects, Q1 and Q2, and they're going to create an electric field at this point, A. They really actually create an electric field everywhere. In this whole entire region, they create an electric field. But we're interested specifically in the electric field right here at point A. Okay? Find the electric field at this point, and then what force is exerted on a test charge that's at this point. All right, so we're going to set a positive direction in order to do this. And we're going to say, let's do a free body diagram of a test charge sitting at point A. That's going to help us determine the direction of the overall electric field. So here it is. Here's our little test charge. And test charges are always positive. So here I've got Q1. Q1 is positive. Right? And so that means that any test charge that's placed here is going to see this and is going to be repulsed and is going to want to move in the plus I hat direction. So that's the direction of the electric field from this guy. Q2 is negative. And so a positive test charge sitting here at A is going to want to move towards Q2, and that's the direction of the electric field at A from 2. So here's what our free body diagram looks like. We now say that the total electric field at A is equal to the vector sum of the electric field at 1 and the electric field from 2. Okay? This is exactly what we did before, but now instead of writing F net equals F1 plus F2, we're writing the electric field net overall at point A is equal to the electric field from 1 plus the electric field from 2. All right, so here it is. We know that in general for a point charge, this is what the electric field looks like. Here's the little piece that Q1 is generating. Here's the little piece that Q2 is generating. We substitute our numbers, keeping in mind that this will be plus I hat, this one will be negative I hat, and we arrive at an answer, negative 4.8 times 10 to the 5th newtons per coulomb, and it's in the I hat direction. So it's negative I hat direction, and there it is. So very, very straightforward. Still, terminology, concepts, a little bit tricky. Part B just says, oh, if I have a test charge that has this amount, what's the force on it? Well, then I just say Q times the electric field is what the force is. So I say, oh, well, 4.5 times 10 to the 6 times 4.8 times 10 to the 5th, and I get negative 2.2 newtons. Force in the same direction as the electric field. All right, next lesson, more complicated E fields.